Hello, welcome to a portrait of linear algebra. This is Jude Socrates, and our video for today is about linear transformations. So when you hear the word transformation, you think you're going to change something. And that's probably a good description of what we're about to do. We're going to take vectors and we're going to transform them. We're going to change them, maybe a little bit, maybe a lot, into something different. So in the video, we're going to find out exactly what is a linear transformation. And we're going to find out that they can actually be described, or more precisely, represented by matrices. We are going to look at special families of matrices called elementary matrices. And we're going to see how to visualize operators on the Euclidean plane R2. In the next video, we're going to see that we can also visualize operators in R3. Now, a linear transformation is a function, but of course, we're going to input into our functions vectors instead of scalars or numbers. So let's first generalize the concept of a function. Exactly what is a function in general in mathematics? So we start with two sets, x and y. A function f from x to y is a rule or a recipe or a formula that receives as its input an element little x of the set capital X and assigns to little x as its output a unique element little y of capital Y. As usual, we will write y equals f of x, and we will call y the image of x under f. We will call capital X the domain of our function f, and capital Y the codomain of f. You're probably expecting the word range, but that will come a little later. We also call f a map because it tells us where to go, and we say that f maps x to y. And more generally, f maps capital X into capital Y. So, as I mentioned, we are going to transform vectors. So our domain and our codomain will both be Euclidean spaces. So the symbol that we will use instead of f and x and y, we will call our linear transformations in general capital T, and they will go from Rn to Rm. So we will pronounce this as T is a transformation from the domain Rn to the codomain Rm, or a shorter way to say that is that T goes from Rn to Rm. We will write T of V is W, or backwards, W equals T of V. So the input for our transformation is the vector V from Rn, and the output of T is a vector W, this time from Rm. However, a linear transformation is more than just a function. It has to fulfill or satisfy two properties, and the names of which we have actually seen before. So a linear transformation T from Rn to Rm is first of all a function, but it has to satisfy that for all vectors u and v from the domain Rn, and for all scalars k, we have the additivity property. So T of the quantity u plus v has to be the same as T of u plus T of v, and we have the homogeneity property. T of k times u has to be k times T of u. So we also say that T is additive and T is homogeneous or homogeneous. In the special case when T has the same domain as codomain, so it goes from Rn to Rn, the same space, we call T a linear operator, or just an operator. If T has codomain R, which we symbolize as R1, in other words, T goes from Rn to R1, we also call T a linear functional. So we have in these two diagrams an illustration of these two properties. So in additivity, in the domain in Rn, you have the two input vectors, v and w. You can add them together. So we've seen this before. Complete the triangle. That is v plus w. How do you satisfy additivity? Well, V gets transformed into T of V, this time in Rm. W transforms into T of W. Now, also complete the diagram. If we connect the tail of T of V to the head of T of W as usual, that should be T of V plus T of W. So the additivity property requires that this third side of the triangle should also be the image of V plus W under T. So in other words, triangles transform into triangles. What does homogeneity look like? Well, you have V in the domain, multiply it by a scalar K of V, K times V. So you might maybe double the length if you multiply by 2, but the two vectors are parallel to each other. V transforms into a T of V. K times V will transform into T of K times V. But homogeneity says that if K of V, let's say, is twice V, then T of KV has to be twice T of V. So in other words, parallel vectors stay parallel and their constant of proportionality stay the same. Okay, so here's our first example of a linear transformation. We have T going from R3 to R2. So the input vector can be written as XYZ because our domain is R3. Where will XYZ go to? So we will create a vector in R2 and it will show us how to make that vector. So in the first component, we will take 5x minus 3y plus 2z. And in the second component, we will take x minus 4z. So notice there is no y in the second component. And there's nothing wrong with that. Okay, so let's do these four things. Let's find t of negative 2, 3, 7. So let's compute. Let's just put it over here. Where will negative 2, 3, 7 go to? So let me make a copy of that. And we only need two components because we're going from R3 to R2. Okay, so let's blank that out. And maybe I'll make a copy because we are going to do another computation in part B. So, negative 2, 3, 7, negative 10 minus 9, negative 19 plus 14. So I believe that that is negative 15. Okay, so I'm sorry, negative 5. That's right, minus 10 minus 19 plus 14, just minus 5. All right, what about x minus 4v? So we have minus 2 minus 28. So that is, I believe, minus 30. Okay, so the output for this input vector is negative 5, negative 30. Okay, what about 0, 0, 0? Okay, so everything is 0, so that should be easy. 0, 0, 0. So we just get 0. And then we have 0 minus 0. So we just get 0. Okay, so maybe that's not a surprise. When the input is the 0 vector, the output is the 0 vector. So this is actually one of the properties of linear transformations, which you're going to do in the homework in 3 different ways. The input, when the input to a transformation is the 0 vector of the domain, the output is the 0 vector, but the 0 vector of the codomain. Okay, so let's now show that T is both additive and homogeneous. So we need 2 input vectors, u and v, and we have to show that if you add them together first, you make u plus v, and then transform u plus v. It will be the same as t of u plus t of v. Transform u and v separately, and then add them together. Okay, so we have to build the 2 sides of this equation. And here's the formula that we have up there. Obviously, I just copied it. So we need two input vectors. So what I'm going to do is I'm going to make some more copies. I need two different input vectors, though. So to do that, I will make the first vector x1, y1, z1. So its output is just 5x1 minus 3y1 plus 2z1 and x1 minus 4z1. Okay, so I'm going to do the same thing with a second vector. So I will make x2, y2, z2. Okay, so the output, of course, is 5x2 minus 3y2 plus 2z2, x2 minus 4z2. Okay, simple enough. Now we are going to add them together. So our right side, let's work on the right side. Our right side is P of u plus P of v, and that will be P of x1, y1, z1 plus P of x2, y2, z2. Okay, so we're just going to copy these two vectors here. Okay, but we know how to add two vectors. So this is simply the first vector, and then we add this to the first component. So we need plus this, and then we take this, and then we add it to the second component. Oh, whoops, I'm sorry. So I copied the wrong thing. So that should be this one. Like, why are they all ones? Here we go. So that's better. And we have this. Okay, I call that a copy and paste fail. Okay, so now, is that the same as P of u plus v? All right, well, what is u plus v? It's just x1 plus x2, y1 plus y2, z1 plus z2. Okay, so do we find those expressions in here? Well, oh, there's a 5x1 here and a 5x2 there. So of course, we can bring them closer to each other. So let's scoot 5x2 over here, and then minus 3y2 scoot over here, and 2z1 plus 2z2 are together. How about the second component? x1 plus x2 minus 4z1 minus 4z2. All right, so finally, we can now bring just the perfect amount of space. The x1 and x2 together, so the 5 factors out. The y1 and y2 together, so the minus 3 factors out. That becomes a plus y1 plus y2. And we have z1 plus 2 z2. That just becomes z1 plus z2. x1 plus x2 is already together. And we have z1 plus z2. Okay, so of course that is our P of u plus P of v, because u plus v is just x1 plus x2, y1 plus y2, and z1 plus z2. Okay, so how about homogeneity? There's only one input vector u, but we have a scalar times k, right? So we don't need subscripts. So reminder, this is what P does. So this time we will input k times u. And we can easily do that by replacing x, y, z with kx, ky, and kz. Okay, but what does that mean? Instead of 5 times x, we have 5 times kx. Instead of minus 3y, we have k times y, and we have k times z. X becomes k times x, and z becomes k times z. Okay, so every component, every term, gets an extra x. So of course, we know the distributive property for real numbers. Oh, but wait, hang on a second. Let's think about the associative property first. So we can put k outside the parenthesis and put the 5 inside. Ooh, okay. Put the k outside. In fact, let's put a plus k and put the minus 3 inside. K outside, 2 inside. K is already outside, plus k outside, and minus 4 inside. And you might be thinking, can't you just take the k outside? Yes, but I really want to see why things happen in mathematics. Okay, now we can see that each of these terms has a k, and so let's use the distributive property for real numbers. We can put the minus 3y inside and the plus 2z inside. So this whole term gets multiplied by k, and similarly we can put x and minus 4z together. Okay, so we're back in chapter 1, scalar multiplication. We can take the k all the way outside of that vector. So we have k times the first component and k times the second component. And of course, we recognize this as the original transformation, the formula for t of x, y, z. And so that is simply k times t of x, y, z. So our transformation is indeed homogeneous. Yay! Okay, now before we move on, let's do something different, slightly different. Let me put a plus 2 on the second component of the output vector. Is it still additive? Is it still homogeneous? Okay, so I copied our homogeneity proof. So we have t of xy, kx, ky, and kz. So replace x, y, and z with k times that component. But we have an extra plus 2. That plus 2 does not have a variable attached to it. Okay, if it had been 2y, then that y would have been replaced by k times y. Okay, but it's not. It's just plus 2. So there is no extra k, rather. So the right side is not k times t of x, y, z. So therefore, unfortunately, this function, it's still a function from R3 to R2, but it's not homogeneous. So therefore, it is not a linear transformation. Okay, so we're going to do one more thing with this example, and that is we're going to rewrite it. So I hope you remember when we talked about multiplying a matrix by a vector, we said, let's take the vector, which we usually write horizontally, and let's write it vertically as a column matrix. We're going to do something similar. So instead of x, y, z being horizontal, we are going to turn that vector into a column matrix. So I'm going to put a 3 by 1 column matrix, and let's put brackets so it looks nice. So let's put x, y, z inside. Okay, and then we're going to write the output vector also as a column matrix. So this time I only need a 2 by 1. So let's see. Okay, there you go. I can copy that. And the formula says 5x minus 3y plus 2z in the first component, and x minus 4z in the second component. Okay, so what are you going to do now? Well, we see three variables, x, y, and z, three symbols inside that matrix. So let's decompose. Okay, so I'm going to make 3 copies of that, and we've done this before. Let's put only the x's in the first matrix. Next, let's put only y's in the second. Oh, there's no y there. 0. And z's only in the third component. Okay, so only x, only y, only z. All right, and do you remember what we do next? Do you? We factor out the variables. So this is x times 5. Ooh, don't forget there's a 1 there. Y and minus 3 there. And z, 2, negative 4. Should we factor out the 2? No. Just the variables. Okay, now we have a linear combination of 3 column vectors. I think I may have given it away earlier. That should remind you of just a matrix product. Okay, so the coefficients are x, y, and z, and on the left of it, there should be a matrix. How big should that matrix be? Well, there are 3 columns. Each of them is from R2. So we need a 2 by 3 matrix. So 5, 1 in the first column, minus 3, 0 in the second, and 2, minus 4 in the third. So what does this tell you? If you want to know where x, y, z goes to, you just multiply x, y, z as a column matrix to this matrix, which has 5, 1, minus 3, 0, and 2, minus 4. I read that vertically. Let's read it horizontally. 5 minus 3, 2. 5 minus 3, 2. Looks familiar. 1, 0, minus 4. 1, there's no y. 0, minus 4. All right, so let's take this matrix product for a test drive. The first thing we did was we found what is t of minus 2, 3, 7. And remember, I made a mistake. I thought it was minus 15, minus 30, but it was just minus 5, minus 30. Okay, so this equation tells us that if we want t of negative 2, 3, 7, all we have to do is perform a matrix product. So multiply these two matrices together. And of course, you shouldn't trust me because I do make mistakes. So let's make the computer solve this for us. What is that? Minus 5, minus 30. The computer never lies. Just kidding. Sometimes it's a liar. So we did correct our mistake, and we have the correct answer, minus 5, minus 30. Okay, promise. One last thing before we move on. This is the definition of our transformation. We found this matrix, and we said, if you want t of x, y, z, just multiply that matrix by x, y, z. So let's input our 3 standard basis vectors for R3, our domain. 1, 0, 0. How much simpler can it get? We already did 0, 0, 0. It was boring. The output was 0, 0. Oh, of course, if that were all zeros, you'll just get 0 plus 0 plus 0, the 0, 2 vectors. So what about 1, 0, 0? So 1, 0, 0, you multiply column 1 by 1, the other two columns do not contribute. So it's just 5, 1. Okay, how about 0, 1, 0? You take 1 times column 2, the other two columns don't contribute. So we get -3, 0. 0, 0, 1. You take 1 times the third column, the other two columns do not contribute. So we get 2, -4. Okay, so what's another way of thinking about this? If you want the first column of this matrix, just plug in 1, 0, 0 into your transformation. 1, 0, 0, we get 5. 1, 0, you get 1. And so on. Okay, so finally, we can move on and generalize the example that we just saw. This is a very important theorem, and it tells us that basically every linear transformation can be represented by a matrix, and conversely, if you are looking at a matrix, then you're actually looking at instructions on how to create a linear transformation. So, this theorem says that a function t from Rn to Rm is a linear transformation if and only if we can find an m by n matrix A so that the action of t can be performed by matrix multiplication. T of x is simply A times x, where on the right side we view x from Rn as an n by 1 matrix, just like we did when we converted xyz into xyz. And T of x, the output vector from Rm, is also a matrix, but this time it's an m by 1 matrix. So we've seen this happen. You multiplied that 2 by 3 by a 3 by 1, the answer is a 2 by 1. So the matrix, the size of the matrix that we multiplied A with is not necessarily the size of the product, A times x. So we refer to A as the standard matrix of T, and we write this symbol for A, the matrix of T. So we've kind of seen that symbol before, but we used matrix of S when we had a set of vectors. So hopefully, if the context is clear, and it should be, then there should be no confusion between matrix of a set of vectors versus matrix of T. Okay? However, in the columns of this matrix A are T of E1, T of E2, up to T of En. Where do the standard basis vectors go? We looked at 1, 0, 0. Where does 1, 0, 0 go? 5, 1. So that should be found in column 1. So in a sense, this is the matrix of a set of vectors, and those vectors are T of E1, T of E2, up to T of En. Now, since T is a function, the matrix of T has to be unique. Column 1 has to be T of E1, and so on. So the standard matrix of T is unique, and if B is another matrix such that T of x is also B times x for all x in Rn, then A and B have to be exactly the same matrix. So we say that A represents T, or A is a representation of T. In particular, if T goes from Rn to Rn, namely it's an operator, then the matrix of T is an n by n, or a square matrix. And if T is a linear functional, the codomain is just R, then T is a 1 by n, or a row matrix. Now, I hope you noticed, let's go back to the theorem. I hope you noticed that the dimensions of the domain and the codomain flip. So the domain is Rn, the codomain is Rm. The matrix of the transformation is m by n. All right, so n is first here, m is second, but when we put together the matrix, they switch. So it's an m by n matrix. So let's think about our example. We went from R3 to R2, x, y, z transformed into a vector with only two components. And the matrix that we got is 2 by 3, not 3 by 2. So the proof of this theorem is not that hard. Let's do the backwards direction first. So suppose you have this matrix A, so that t of x is just 8 times x. What is t of x plus y? We have to show additivity and homogeneity. Well, x plus y is now our input, so t of x plus y is 8 times x plus y. But let's go back to chapter 1. We have the additivity property for matrix multiplication. So 8 times x plus y is just ax plus ay. So who is ax? It's t of x, and ay is t of y. So that's just t of x plus t of y. And similarly, what happens to kx? You multiply it by a, and you have the homogeneity property for matrix multiplication. Same word. So you can take out the k, bring in the a, but a times x is our t of x. So therefore, that's just k times tx. Now, the forwards direction is a little bit tricky, but it goes back, all the way back to section 1.1. If you have a vector from Rn, x1 to xn, we can write it as a linear combination of the standard basis vectors. That's the key idea to this proof. So what happens to x under t? So replace x1 to xn with x1 e1 plus x2 e2 through xn en. And then we apply t. So t is additive, which means that basically we can distribute t to each of these terms. So that becomes t of x1 e1, second term becomes t of x2 e2, and so on. And then we use homogeneity. We can take out x1. So the first term is x1 times t of e1. The second term is x2 times t of e2, and so on. Now that's a linear combination of t of e1 through t of en. But that's just the definition of a matrix product. We can collect these vectors into the columns of a matrix and the coefficients into a column matrix. So that linear combination is just the matrix product, where the matrix is t of e1 through t of en in the columns, and the vector on the right is x1 to xn. So that's just 8 times x. Okay, so let's take a look at some easy examples. You might almost say they're trivial examples. Well, the first one is definitely trivial. We have the zero transformation. Let's write it as z sub 2 comma 4, because we will go from R2 to R4. So of course you can make one with any codomain, any domain and any codomain. So where will x1, x2 go to? As the name implies, the zero transformation will take any input vector and will always output the zero vector in the codomain. So that is 0, 0, 0, 0. Very boring, very trivial. So in other words, z sub 2, 4 of x is always 0, 4 for all x in R2. Gosh, what would the matrix of this transformation look like? So we always want to output 0, 0, 0, 0. Can we multiply x1, x2 by a matrix? How big should that matrix be? So we're going from R2 to R4. What did we say? You got to switch. So we need a 4 by 2 matrix, 4 by 2. So that when we multiply that matrix by x1, x2, everything becomes all zeros. Gosh, that is such a hard problem. Hell no. That is just the zero matrix. So if you multiply this matrix by x1, x2, everything just turns into zeros. So that is, of course, a linear transformation. Okay, this next example is also easy. but maybe trivial is not the right word for it. Okay, so I started the video by saying that when you think of the word transformation, you think of changing something. Well, here is a function that takes an input vector from R3, x1, x2, or x3, and doesn't do anything. The output is exactly the same as the input, okay? So that's why it's called the identity. The identity operator again just means that the domain and the codomain are exactly the same, and the output is exactly the same as the input. Ith sub R3 of x is still x for all x in R3. So it doesn't do anything. Okay, it's not exactly a transformation, you might say. It doesn't transform anything, but we'll still call it a transformation. So, how can you make a matrix for this transformation? Well, let's guess, okay? If this were a transformation, it would have a matrix, and in column 1 will be the image of 1, 0, 0, our first standard basis vector in R3. Where will 1, 0, 0 go to? 1, 0, 0. So 1, 0, 0 should be in column 1. Okay, where will 0, 1, 0 go? 0, 1, 0. So 0, 1, 0 should be in column 2. 0, 0, 1 should be in column 3. Okay, have we seen a matrix that looks like that before? Oh yeah, oh yeah. We called it the identity matrix. In this case, the 3 by 3 identity matrix. So let's check. If this matrix is the right matrix for our identity operator, then if you multiply it by any x, y, z, you should still get x, y, z. I wonder if it will work. Well, first the letters have to be correct. Multiply them together, boom, of course. X times column 1 is just x. Y times column 2 is just y in the second component. Z times column 3 is z in the third component. Add it all together, we get x, y, z. Okay, so this one is definitely not so trivial. Okay, so let's create what's called a scaling operator. So S for scaling, and there's a subscript here, -2. It will again go from R3 to R3. And again, it can go from R5 to R5 and so on. Here's the idea. So the input vector is x1, x2, x3. The subscript is -2. That just tells us multiply every component of x1 and x2 and x3 by -2. So in other words, s sub -2 of x is just -2 times x, okay? So it's just like scalar multiplication, okay? Just multiply x by -2. So again, let's guess. If this really is a transformation, it should have a matrix. Where will 1, 0, 0 go to? -2, 0, 0. So instead of 1, 0, 0, you have -2, 0, 0. But 0, 1, 0. 0 minus 2, 0. Ooh. So it looks like it's just like the identity matrix, but instead of 1, you have -2. So this should be the matrix of S sub -2. And you say, that looks so much like the identity operator, doesn't it? And yes, in the next video, the next section, we will show that, yeah, a logical thing would be call this -2 times I3. So we will, of course, define what it means to multiply a matrix by a scalar. I think you already know, right? Just multiply every entry in that matrix by that scalar. Okay, so we're going to look at a special family of matrices, which are called elementary matrices, and we're going to define them first in general, but we're also going to look at what they do on the Euclidean plane, R2. So, An n by n matrix E is called an elementary matrix if it is obtained by performing a single elementary row operation on the identity matrix I sub n. So if you recall, there are three kinds of elementary row operations. So type 1, multiply row I by a non-zero scalar C. Type 2, exchange two rows. Type 3, add a multiple C times row J to row I. So because these are n by n or square matrices, they represent operators. So they will transform Rn into Rn. So let's look at some examples. So we will start with the 3 by 3 identity matrix. And let's create these three elementary matrices. I have a -4 here. So that's 1 turned into -4. Okay, so what did we do? Multiply row 2 of the identity by -4, and we get row 2 of this elementary matrix. Okay, start fresh, start over. Start with the identity matrix untouched. Now we're going to change it. I have 0, 0, 1 here, 0, 1, 0, 1, 0, 0. So 0, 1, 0, that's the same second row as the identity matrix, but 1, 0, 0 is now at the bottom, 0, 0, 1 is now at the top. So what happened? You just exchange row 1 and row 3. That's a single row operation. So E2 is elementary. What about E3? It's almost the identity, but there's a 7 over here. How can we make that 7? So it's not multiply row 3 by 7, because that would turn the 1 into a 7. No, the 7 is in the wrong place. So what do we have to do? That 7 has to come from row 2. So we will multiply row 2 by 7, and we will add it to row 3. So that is also an elementary matrix. So each of these is a separate type, type 1, type 2, and type 3. Okay, so what about these guys? No, they're not elementary. Why not? Well, there's a 2 here and the -4 here. That's two operations, two type 1 operations. Multiply row 1 by 2, multiply row 2 by -4. So that's not elementary. This looks like you just exchanged rows. Oh, this is row 1. It came from row 1. That's row 3. That's row 2. So it's not a single exchange. It's two exchanges. So to bring row 3 up here, you can switch with row 1, but row 1 would be at the bottom. So to bring row 1 to the second row, you have to switch with row 2. So that's two swaps. That's not an elementary row matrix. So similarly here, if you want 3 and -2 on the third row, you need 3 of the first row added to the third row, -2 of the second row added to the third row. So that's two elementary operations. That's not elementary. So let's drop down and look at 2 by 2 type 1 elementary matrices. So starting with the identity, 2 by 2 identity, multiply one row by a non-zero constant, so row 1 times C, or row 2 by C. So it turns out that these are what are called horizontal or vertical dilations or contractions. So let's take a look at this one. Starting with identity, we multiplied row 1 by -3/4. Row 2, we don't do anything. If you do something, it's not elementary anymore. So what we're going to do is we're going to go to GeoGebra and we're going to see what happens to R2 because of this operator. So reminder that in column 1 of this matrix, you will find T of E1. What happens to E1? E1 is 1, 0, it turns into minus 3/4, 0. What happens to E2? It's in the second column. Oh wait, that's still E2. So only E1 changes. E2 does not change. Okay, let's go to Algebra. Okay, so the first thing we're going to do is we're just going to draw E1 and E2. So here is vector, and the point is 1, 0. Okay, so there's E1 on our screen. And let's draw 0, 1. So there is E2. Okay, so what we're going to do is we're going to complete this square. So I have this polygon command. So all we do is click on points, and we are going to complete a square. Oops, back to the starting point. Ooh, okay. So that square is what we call our basic box. Okay. Notice that there's a third corner, which is not part of our two vectors, but who is that third corner? That is just the vector 1, 1, which is the sum of 1, 0 and 0, 1. So there is the vector 1, 1. Okay, so we call this our basic box. Okay, we're going to use this picture to try to understand what happens to R2 under these transformations. So whatever happens in here will be transformed by our operators. Okay, so what I'm going to do is I am going to draw freehand. So I'm going to take a pen, and I'm going to use, of course, my favorite color, which is red. And I'm going to draw very badly the letter R inside this basic box. Okay, so of course we can draw anything, any figure inside this basic box. But I like the letter R of all the letters in the alphabet because it has no symmetry. So in other words, if you do something to it, if you change it somewhat, your brain can pick out, ooh, what happened there. Okay, so now we're going to see what happens when we do our contraction, or maybe it's a dilation. So our matrix is negative 3/4, 0, 0, 1. So we said that in column 1 is hiding our transformation for E1. So E1 turns into the vector negative 3/4, comma, 0. Ooh, okay. So there is our vector for P of E1. And we said E2 doesn't change. So the output for E2 is still 0, 1. Okay, so that's U. That is our negative 3/4, 0. And V is 0, 1. So let's play the same game. Okay, so let's complete the square. Oh, it's not a square anymore. It's a rectangle. So starting with origin, let's go to U, and then let's go up here, and then connect there, and back to A. Okay, so that is the image of our basic box. So remember, of course, it was over here. It was 1 by 1 square on the right, but it's now over here on the left. Okay, we had the letter R written rather badly inside the basic box. What will happen to it? Well, the vertical part of the R is attached to our 0, 1. Okay, and the foot of the R is attached to 1, 0. 1, 0 moved over here. So that is where the foot of the letter R should go. So let's draw. Maybe I will have better luck this time. And how about, let's use blue this time. Okay, so the letter R should look like this. Here we go. So it is, I hope the word reflection is coming to mind. It is reflected across the y-axis. Okay, and yeah, now you see what I'm saying about your brain figuring out what happened. The R flipped over. Okay, if you did this to the letter A, for example, it will still look like the letter A. But your brain is telling you, wait, something's wrong here. We didn't just move the R to the left and then shrank it a little bit. No, it had to be flipped over, and then the X width got contracted, shortened a little bit. So dilation is the opposite. It will lengthen a vector instead of shortening it. Okay, so for our last example, we are going to look at what are called shear operators. So again, start with the 2 by 2 identity matrix, but this time we will add a multiple of one row to another row. So if there's a C up here, it means that we need row 2, multiply row 2 by C, add it to row 1. If the C is down here, then we multiply row 1 by C, and we add it to row 2. So let's take a look at this matrix. Okay, so we still have that negative 3, 4, but this time it's in the lower left corner instead of the upper left corner. So the upper left is still a 1. It's only this entry that changed. Okay, so before we go back to GeoGebra, okay, let's review. So again, column 1 is hiding in plain sight what happens to 1, 0. So it's no longer 1, 0, it's 1 minus 3/4. Okay, so the 1 stays, but there's now a y component, a non-zero y component of negative 3/4. How about 0, 1? Oh, 0, 1 is still 0, 1. So just like our last example, E2, what we call J, does not change. All right, so let's go to GeoGebra. We have to remember 1, negative 3/4. Okay, so here's another fresh copy. So we need 1, negative 3/4 for our first vector. 0, 1 does not change. So we need vector 0, 1, comma 1. Okay, so let's make our polygon. So, okay, so this is a little bit trickier. Where is the third vertex? Okay, so before it was kind of obvious that it's still a rectangle, but now, where is third vertex? Well, so remember what happened. The square, that upper right corner was 1, 1. And that's because we have 1, 0 plus 0, 1. You make 1, 1. So all we do is add these two vectors together. U plus V. Ah, that is where the third corner is going to go. So polygon, start over here, and then walk this way, and then walk this way, walk this way, and back to the origin. Ooh, there we go. Okay, so that is the image of our basic box. Okay, so 1, 0 is now dragged down here. Okay, so we're going to draw that R. Right? Originally, it's just the R, which is inside the square here. But, okay, what's going to happen? So again, the vertical member does not move, okay? And the foot of the R is going to move. So it's now going to get dragged down here. Is the R going to flip though? I don't think so, because the top of the R should still be here and the foot will be down there. Okay, so let's try. And what color shall we use this time? Oh, how about green? Okay, so the vertical portion, that's probably my best one so far. Okay, and then the top of the R goes this way. Okay, there you go. And then we need the leg. So the leg has to drop down over there. Aha, okay. So that is the image of our letter R, okay? This is called the shear operator, okay? So basically it means that you take your square and then you drag down one corner a little bit, okay? So it's a vertical downward shear. You can also shift it up, so it will be a vertical upward shear. You can also shear along the x direction. So you can make the parallelogram go this way, or you can make it go the other way. Okay, so those are all examples of shear operators. All right, that's our video. Thank you very much for watching. Once again, this is Jude Socrates, and you will find me on Facebook. You will find the 4th edition on Facebook, as well as at kendallhunt.com. So in our next video, we are going to see examples of operators in R3. So until next time, enjoy the rest of your day.